Here's one thing I like. You can just go up here to the top, and you can go to design and quick layout. And that's my quick layout. It's my favorite one. You can also get to the chart title, all this stuff. Okay, also, I'll show this again real quick. Look at all these options. We've got so many cool things. It's so nice.
Gary! I was just looking for the sports channel, Gary.
Hey everybody, we are live here on YouTube again. Who do we have in the chat? Can everyone hear and see me? I'm hoping everything is streaming properly right now through everything working. It looks like it's all working properly. Who is here? We're gonna start doing some review of the concepts. I might answer a question in the chat. Hey, Sydney. Hey, so everyone, we can hear and we can see me. What questions are there about the test? Let's see what questions there are. Everything is good. Glad to hear that. Hey, I know. I'm sorry. It's just I got no Julio. Oh, so the weakest related, but when I run an M-string, it has the lowest coefficients in the output. Be careful looking at those coefficients, Kyle. Make sure there's a lot of ways to look at them if you're trying to find the weakest. Yeah, maybe there's a lot of ways. Make sure to think about what those coefficients mean. Think about what those coefficients mean. I think you're onto something right there, Kyle. So that's the best I can get. I can't tell you the answer to it. So that we're starting with the 320 question strong right there. So you're saying in the visualized model you see one thing, but then with the coefficients you see something else. I'm so sorry. I got this shirt at Goodwill for like $2. It is like one of the like soft shirts. Like you give me a soft shirt and I'll wear it. So I was a big fan of the Braves growing up. I was a Braves fan. Tommy Glavine, David Justice. That's how I know David Justice. Had that poster on my wall growing up. And we were in, there we go. Okay, so we're okay with that. It's kind of a nice, it's got some symmetry to it. I will give you a shirt if you answer the question. A really soft one. Which chapter is on the exam the most? Oh, that's such a great question. Here, let's hop over here. Let's go over to the review stuff. Yeah, we've got the review assignment right here. Remember that the test is covering a lot of really great stuff. So glad to see everybody in the chat right here. I can draw on the screen again. Perfect. Life is good. So the test chapters start with the proportion test and go all up the way to the chi-squared test. And how about the rats? Which one is the rats on the review assignment? What number is the rats one on the review assignment? Are you talking about this right here? Which number on do you guys want to do? Which number on the review on this right here do you guys want to do? Which number do people want to do? So we're going to be going over different review questions. I hear the rats one. I don't know which number that is off the top of my head. A lot of times context to questions aren't as important to me. I'm always trying to work. Number two. It could be rats, it could be dinosaurs, it could be anything. Let's see right here. Is this right here? Are you talking about this review assignment? So this review assignment right here, there might be a separate thing someone put out. Might need to email that to me or something. But this is what we have right here. And we have right here the 3 conditions for a confidence interval. And we can do our confidence interval and all this stuff. Let's start with some global stuff right here. People always ask me, I've got way too much stuff open right here. Let's talk about the conditions and the different conditions we have because this is really great stuff to memorize. I'm going to change the layout right here. We're going to go to orientation landscape. So let's talk about the different conditions. This is a really quick, good review. And I don't see the rat one on there. That might be a totally different review and totally different question. So when you think about this right here, we're going to set up our conditions like this. I'm going to have to zoom out a little bit. Oh, that'll be good right there. We need to zoom out a little bit. Let me try this all again. You ready? So we have right here our 4 conditions. There we go. Now we got 4 conditions. First test, second test, third test, fourth test. Okay. It's number 1 on my exam 3 review. Oh, it's like the review assignment. Oh, review assignment. Yeah. We might come back and do that here in a moment. Yeah, it's a good question. The review assignment. Yes. This is 1 proportion. We'll come back. We'll do that here in a moment. Yeah, we'll do that one as a review question. And this is 1 mean. So this is 1 mean right here. This is a t-test. This is 2 means. And this is a 2-sample t-test. That says 2-sample t right there. and then this is chi-square. And when we do these conditions right here, I always like to say condition 1 is random. Let's go to the big red pen right here. Condition 1 is going to be random. You have to randomly select. So condition 1 is random. Condition 2 is 10%. So it doesn't matter, whenever you hear, if you watch any of my lectures, I say condition 1, it's that we randomly select the observations we are taking. Condition 2 being 10%, those are things we do every time. But I want us to notice something about these variables right here. Who here in the chat can tell me both of these tests are dealing with a what y variable? Both of those tests right there are dealing with a what kind of y variable? Where this one over here, let's differentiate by color. Who knows what the tests I circled with the mean tests are? The tests right here are dealing with a quantitative y variable. And this is dealing with a categorical x, and this one is two categorical variables. So this one is categorical dash categorical, which is one of our conditions coming up right here. So if you notice right here, the t-tests are quantitative. Anytime you do a t-test, you have to be predicting a quantitative y. Like a one-sample t-test is let's examine the heights of UT students. A two-sample t-test is let's understand the heights of UT students and Florida students and compare those. Do you see why the difference is between the one and the two sample? Let's compare the heights of UT students. Let's compare the heights of UT students and Florida students to see if there's a difference. That's why it's called a two-sample t-test, and we're dealing with the mean of Florida students and the mean of UT students. So it's instead of one group having their mean tested, you're testing the difference between the means of two groups, hence two-sample means test or two means, two-sample t-test. So when we look at these, we have to understand this because this is going to direct us on the conditions. The conditions right here will be success/failure. And right here will be nearly normal. And you know what we can do? We can write this across these. I want to make sure it's obvious. And then this would be nearly normal. Oh my gosh, not an N, an M. Nearly normal. There are no numbers to these conditions, two samples right there. So if we wanted to compare the Cardinals to the Rangers or the Cardinals to the Yankees, I'm trying to think who else you played for. I think Rangers, wait, and Orioles, right? Orioles. There we go. I've got family up in Baltimore. So this would be nearly normal. The Cubs, there we go. The Chicago Cubs, there we go. So the two sample and the Orioles, there we go. And so we have here the third condition is nearly normal for quantitative data, and that's when we draw like a histogram right here and we look at to see if the histogram is nearly normal. So we'd get a histogram from both of these. And the thing is, when we do the two sample, we get two histograms. We get a histogram for both groups, so we need to see that the histograms are nearly normal. That is our goal with these right here. We get two histograms right here for this test on nearly normal. So make sure you know that when you do the two sample t, you want to get two histograms. You're going to look at both distributions to see if both distributions are nearly normal. So that is what we're doing right there, the nearly normal condition. And this right here, we want all the success failures to be greater than or equal to 10. The chi-squared's third condition is expected cell count. Is that going behind my head? Not yet. You can be greater than or equal to 5. If it's exactly 5, don't worry, we don't do that on the test, but expected cell count greater than or equal to 5. So that's right by my head right there, expected cell count. And last but not least, we do have a fourth condition. So the fourth condition only applies to the last few things. The fourth condition here will be independent means. The bright lights zap your memory. Independent means, and this is count data. I figure this is a good place to review what's going on right here, to make sure you see all the conditions in my glorious handwriting, best I can do. But random is the first condition for all of these. We need to randomly collect our data. 10% is the second condition, which means we need to take less than 10% of the total population. The third condition depends on the variable type that we have. If we have categorical data, it'll be success failure, and if we have quantitative data, it'll be nearly normal. Success failure means that we need to have at least 10 successes and at least 10 failures, often found by the formula NP0 or NQ0 when doing a statistical test. Nearly normal can be judging the histogram to see if it's nearly normal. Now, if we have a larger sample size, the distribution of the mean, which we're analyzing the mean, we're not analyzing single observations, we're analyzing the distribution of the mean, will be more normal according to the central limit theorem. So you can have some skew if it's around 25, 40 observations, some skew is fine. But if it's extremely skewed, you want to have at least around 100 observations to make the distribution of the mean nearly normal. I still don't understand the cell count. Great question right there. We can go to that next because that's kind of a good way to work backwards on what do we mean by expected cell count. Expected cell count is that we want at least 5 expected cell counts in all of our cells. Now let's talk about that here in a moment, and we'll mention what count data is. Count data is satisfied by what? How can you say we know that it's count data? How do we know for certain that we have count data when we're doing the chi-squared test of independence? There we go, Adriana, great answer in the chat. It is count data if both variables are categorical. Oh no. I'll be there around 4:30. 4:30. Good questions in the chat. So that is the conditions right there. That is the condition. These are the conditions for all of your tests that you are doing. And let's see next right here. So now the question is, how do we get those expected cell counts? Well, this is a good way of working backwards from what we've been doing to talk about the chi-squared. The chi-squared, let's look at something right here. You think Brian has favoritism towards people who like anime. So we've got people who like anime and people who don't like anime, no anime people. And we've got the people who pass and we've got the people who fail Brian's class. Does that make sense? Is this categorical? Because we have anime, yes, anime, no. So I have anime, no anime. And then we have pass and we have fail. So we know in Brian's class that there are 80 students who like anime, and there's 120 who don't. No, I have no idea why. And then, so this right here, so for computational conditions are, and Audrey, great question. It would depend on, is it categorical or if it's quantitative. If it's quantitative, the third condition will be nearly normal. If it's quantitative, the third condition will be nearly normal. So just to make sure it's very, very clear, make sure when you're making your confidence interval, that's the wrong button right there, make sure to look at which one you're doing. If you're doing a confidence interval for the mean, then you would follow, whoops, that's the wrong one. If you're doing a confidence interval for the mean, you would follow through and you would go and do this one right here. So if you're doing one sample mean confidence interval, there is your choice of what to do. If you were doing, which we had on the last test, it won't be on this test, if you're doing one sample proportion confidence interval, you would do this right here. It all depends on which confidence interval you're doing. Confidence interval for the proportion would be that, and confidence interval for the mean would be the next one. Confidence interval for the difference between two means would be this one. If you notice, this is also the conditions for the test or for the confidence interval. If you're doing the confidence interval for the difference between two means. Great question right there. Make sure to notice what your confidence interval is trying to estimate, whether it be the proportion, the mean, or the difference between the means. The proportion, the mean, or the difference between the means. That is correct. One sample proportion confidence intervals are not on this test. One sample proportion tests are on this test. Good question. With this right here, and keep those questions coming. I appreciate you guys are here. You get your questions answered. Oh, there's more sparkly pens than just that? Oh my gosh, I shouldn't have saw that. With this right here, I want you to think about this. 100, this is horrible, horrible news, but apparently, according to what I know, I only have 100 students pass and 100 students fail. Now, I want you to think, how many people who like anime would you expect to pass? One proportion test, one prop Z test is not on this. How many? Oh, we'll go over that next, Hunter. Great question. We will do that next. We'll do a little chi-squared, and then we'll do Hunter's question next. So how many students who like anime would you expect to pass? Now I'm going to make this very simple for you. Think about this. Half my students pass, half my students fail. How many students who like anime would you expect to pass? How many students who said that they like anime would you expect to pass? This will be the observed up here, and this will be the expected. Does anyone know? Just think about this. If there are 80 students who like anime, how many of them would you expect to pass? Out of the 80, if half of them pass, how many would you expect to pass if we would expect half to pass? You are right. You're actually doing the formula right here. Let's make it clear. You're doing these numbers times these numbers over this. This is the formula row total times column total. That's row total times column total over grand total. And if you notice, this formula will be the same for the students who like anime that we expect to pass and fail. Be able to do this and be able to write out this formula and know what you have, that we would get the expected count right here to be 40, and this would also be 40, and this would be 60, and this would be 60. If you're wondering how I got the number right here, it'd be the formula, and try to write it out for yourself. It'd be these two numbers, because that's the row total and column total, times that. Does everyone see I'm doing row total times column total over grand total? This is the row total. This is the column total. Let's make a different color for that. This is the row total. This is the column total. This is the grand total. So we have row total times column total over grand total, and you just need to match the cells to which one they're going to find out the value. As in that 60 I have highlighted right there is the value for that cell for the amount of students who don't like anime that we would expect to pass the class. So let's come up with some fake data right here, and we're going to make it that there's really not that strong of a relationship with what's going on right here. So we're going to put in the value of 50 or 39 and the value of 41, and then we'll put right here 58. I might have done the wrong numbers right there. So I think I'm going to have to, I think this will have to be 61. It has to add up to the numbers down below. And then this will be, can it work? Oh, it can, right? 59, good. I think this works. The numbers down below have to add up to the proper numbers because we have to have 120 going this way and we have to have 80 going that other way. If you notice here, we have very close to the same numbers. All the numbers are very, very close. Now take a moment right here and see if you can get the cell chi-squareds. So now we're going to solve for our cell chi-squareds. We'll go back and answer another question here in a second that was asked that kind of relates to this. Let me not skip the expecteds. The condition of at least 5 expected cell counts can be checked right here, because what would you say about all of these expected cell counts and why we pass? Why do we pass? We pass the expected cell count condition because why? All of the what? Say it in the chat. I love it when people answer in the chat. What is going on right here with all of these expected cell counts? Every one of these expected cell counts is what? Every single one of these expected cell counts is what? Greater than? All expected cell counts are at least 5. They're all greater than or equal to 5. You are exactly right. And technically, the only one we would need to check would be one of these two right here. You would only need to check this one right here because if the smallest one is greater than or equal to 5, then you are good. Imagine if you want to go out to the bar with your friends. And so you know your youngest friend is 23. If your youngest friend is 23 that you're going to go to the bar with, is everybody older than 21? And the answer is yes, because if the smallest one is greater than 5, then all the expected cell counts are greater than 5. And we can do that by taking the smallest row total, the smallest column total, and then doing the equation with those and just checking the smallest expected cell count. So if the smallest one is greater than 5, all expected cell counts are greater than 5. Now these cell chi-squareds are found via the formula observed minus expected squared over expected. If you're taking notes, which I always suggest people to do while watching this, the observed in jump is often called count, hence why it's called count data. The observed in jump is called the count. We just call it observed because it's what we observed, it's how many we count. So this is the observed value right here. It's how many we have. So try doing this in the chat. Try to solve for any of the chi-squareds in the chat right now. If you notice, they're all going to turn out a little bit interesting. I think I can do a few of them in my head right now. They all turn out a little bit interesting. I think they're all very, very tiny. I think this one is 0.025, and I'll show some of the formulas here, 0.025, and I think this one's 0.016 with a repeating, and this one's 0.016. I think that's what we get. Let's show some of these formulas and see what we did and make sure I did my work right. I might have made a mistake. What we get right here is that we get observed of 39. I'm doing this top cell right here. And so we need to take these values and do observed minus expected squared over expected. Observed of 39 minus 40, we need to square that difference and divide by 40. Observed minus expected squared over expected, and that gives us the cell chi-squared. So that is 1 squared, which is 1, divided by 40, which is that right there. Now if you notice, the only difference between these formulas then is in the next formula, it's not 39 that we observe, it's 41. And since it's 41 that we observe, well, guess what? 41, when we observe 41, it still has a difference of 1. So with the observation of 41, it's still just 1 squared over 40. That is solving for these cell chi-squareds. Great question, Caroline. That is all of these cell chi-squareds. Every one of these I'm solving out for gives the individual cells. Notice the numbers that I'm highlighting. I'm trying to erase nice and neat here so we can see which numbers I'm highlighting. But erasing very finely is hard on this. Yes, I got it. So, and I'll erase nice and big right here. There we go. That is the one I'm solving for right now. I'm solving for this cell chi-squared. Note the numbers I'm taking. This observed, this expected, and then I'm solving for that cell chi-squared. Do you think you can figure out the formula I'm using down below for the very bottom ones? See if you can figure out the formula I'm using down below for the bottom ones. I need to take the observed and the expected squared over the expected. See if you can do that right now to be practicing along with me and to see if you can get it. So we need to take the observed of 61, and then we need to take the expected of 60. That once again is 1 squared. Then we need to divide by the expected. So I'm going to highlight the ones we have right here, the observed, the expected, and then you take that difference and you square it. Yes, and then Annie, great question in the chat. I'm going to make sure I did this one correctly in my head because I was solving these in my head. So 1 divided by 60 is that right there. So that is what we have by solving it out. And what do we notice right here? And make sure to square it. Technically, it's technically correct. No, great job, Hunter. You did see that you forgot to square it, but it's 1 squared, so 1 squared is 1. So technically, you would have gotten it right on the test, which is awesome. The observed minus expected square, no, we answered that. Row total times column total is to get all of the expecteds. The expecteds will be used, so this is row total times column total over grand total. That is row total times column total over grand total. Please take a note in the chat. They've got it written in the chat right now. Row total times column total over grand total is the formula for expecteds. The formula for cell chi-squareds is observed minus expected squared over expected. Can anyone tell me the test chi-squared for this now? Can anyone tell me the test chi-squared for this? Does anyone know the test chi-squared? How do you find the test chi-squared? I think I know what it'll be. I think it'll be 0.0833333. To find the chi-squared test statistic, so the chi-squared test statistic is equal to the sum of all the cell chi-squareds. You must take all of these cell chi-squareds and add them together to get it. So we have to take all of those. Nice answer in the chat, Sam. Great job. So we're just going to add those up. All I'm going to do is put my calculator over here so you can see me in the calculator. I'm going to take 0.025. I'm going to add to it 0.025. I'm going to add to it 0.01. Oh, 0.0, if I can type today. Oh, well, there we go. 0.0101166, there we go, plus, there we go, 0.01. And there we go, it's 0.08333. That is the test, the chi-squared test statistic. Nice job, Zach, in the chat. You are right. That is the chi-squared test statistic, and we're almost done with this problem. That was, I know this sounds crazy, that was all of step 2. Step 2 is to find the chi-squared test statistic. Step 3 is going to be to find the p-value. Now, there's not a lot of good ways to test this. Maybe we'll look at some jump output for this. You know what? Let's put this data into jump and see it in jump. So we can easily recreate this data right here, and this will maybe help for some people working on the homework assignments. If you want to enter it in by hand, you can. I think I know the numbers. I'm going to have to need these numbers up here. So we have anime, and we have pass. So we have anime, let's start with that one. Anime, no anime, anime, no anime, and then we have pass. We have pass, fail, fail. Oh, I mixed it up. Pass, fail, fail, fail. Okay, good. And now we need the frequency. I'll make this bigger so you can see here in a moment. I just need it on the screen so I can see, not fru, but FERQ for frequency. And let's do the numbers. I'm going to enter in, there were 39 people who liked anime who passed. There were 61 people, and then 41. If you notice, I'm just entering in my numbers, and 59. We've now put our data into JUMP, so let's make it nice and big so everyone can see. And if you're working any of the problems, this here can help to put them into JUMP and then solve for the answers. Once again, we know how to solve for these answers by hand. Yeah, let's show that. Let's show that right here. Hopefully I didn't make an error there. Let's check it out. JUMP's going to show us if I got the right answers. Does somebody liking anime tell us if they're going to pass the class? Or does it explain? Hopefully I didn't get a wrong answer. Hopefully. Expecteds. There, yep, no, we got the expecteds. Okay, good. I got so worried. Okay, good, we're good. And there it is. There's the answers. So we were working correctly. Heart started to speed up a little bit. I was like, oh no, it's so easy to make a mistake and just solve something incorrectly. But yes. So if you notice here, we have the same output, and I'm going to show you the tricks, and these are the things I suggest on the test. Let's take this JUMP output right here, and let's take a look at it. Okay, so let's go to a new Word document. So here we are with the JUMP output, the pretty much same thing we had going on right here. On the test, this is Brian's big suggestions. Take your numbers, such as row total times column total over grand total, and that should equal up to what? 40, which is the expected value. Everything on row 2 in this output is an expected value. So does that match when people do it right there? You should do 80 times 100 over 200. So I'll do it in the calculator just so you can see and make sure you're punching it in the same way I am. 80 times 120 divided by 200 equals, oh my gosh, what did I do? 80 times 100. 80 times 100 divided by 200 equals. It's so easy to make a mistake, look at it the wrong way, say a number the wrong way in your head. It can happen to the best of us. And do show your work. We do give partial credit. It's very easy to just punch something in wrong and then make a mistake. But write it down, double check, especially the mathematics. Those are the good things to double check at the end. But does everyone see how we're solving the formula for the expected right here? And then we could also do any of the formulas for the cell chi-squareds. The cell chi-squared would be this is the observed and this is the expected. So we just do 41 minus 40, we do the difference squared, and then we divide by the expected. Notice how I'm kind of writing on my output, making it very clear what my observed and what my expected are, so then I can put it up there and make sure I have the right stuff. I observed 41 students who, like anime, failed, and I expected 40 students who liked anime to fail. This is a cell chi-squared of 0.025. And people have already said it, but if we take all of these and add them up, we would get the Pearson. And remember, the Pearson as your p-value. That is the Pearson chi-squared test statistic. Make sure you're using the Pearson chi-squared test statistic. One thing I want to point out right here is we haven't talked about the null and the alternative for this, and we've almost covered this whole chapter in the first 20 minutes of the review. Who here knows the trick? And let's tell people who are watching the video the trick that we always have for being able to write the null and the alternative. Okay, on the test, are you going to have to fill in the blank? There could be fill in the blanks, there could be fill in the blank. We could blank something out. We could be like, what is this value right there? We could do that. Great question. Pretty much, Jessica, great answer. Give me a full sentence. Pretend it says, write out a full sentence for the null and the alternative. Let's put some full sentences in the chat for some practice to make sure you know how to write the null and alternative for this test. Who's got it? Who's got that null and who's got that alternative? So it's once you know the null, it's easy to do the alternative. And Jessica, you are on the right track, but I want to see the full test answer, as though this is a test question, and you're like, I got this. If you notice, I've highlighted between the words, and I'll kind of give this away while we're looking for some answers here. We have an X and we have a Y. We will always do a word between them. The word between them will always be independent. So passing the test is independent of liking anime. Yes! Yes, of someone's views on anime, liking anime, exactly. That is the null, and the alternative would be passing the test is not independent. Perfect. That's all it is you just say independent between them. Julio used to start the class with extra credit right there. Perfect answer. Passing the test is independent of anime. Boom. That's all you need to do. So someone's view on anime is independent of their passing the test, all that good stuff. Excellent answers. Just put independent between them. And for the alternative, put not independent. That is, and Jackson, you bring up some really great questions right there. I'm going to show a lot of tips today on when to use mu or when to use p. And the short answer for that is p is when it's proportions and categorical, and mu is when it's means and quantitative. So if you remember our thing earlier that we had, way earlier, like 20 minutes ago, on this one, we'll put a little side note on this. We're going to go to space pen. This one would be p, this one would be mu, this one is mu1 minus mu2, and this one is independent stuff. So the space pen is trying to show you the right answers right there, that proportion would be p, proportions, mu is means, so when you're doing means, it's mu. So is the independent in the hypothesis use both x2, I think you're right, Hunter. So is when you do the independent means, it's y bar 1, y bar 2. I think what you're saying is right. Maybe rephrase it. My brain's not working 100% on that for some reason. Why is it independent? Good question. So the way the null hypothesis goes, we're going to bring back up the jump output there. Don't check for updates. We're going to go look at this right here. Now, the reason it's the chi-square test of independence, I'm going to give a very short answer on this because it actually goes to the mathematics. I know I said go to that output, but we're going to look at this one better yet. If you think about the way you're actually doing some of these probabilities, it's called the chi-square test of independence because of the way your expecteds are found. When you do an expected, think about this. If half my students fail, which is horrible, sorry, no, half won't fail. We'll be better than that. We'll be better than that. If half my students failed, you'd expect what percent of the students who like anime to fail? If half my students failed, you'd expect what percent of the students who like anime to fail? Think about it. If half my students fail, you would expect what percent of my students who like anime to fail? 50%, half. So with that in mind, that's where this expected comes from. It's actually just multiplying the two probabilities together. And what is the rule when you multiply two probabilities? Like if you figure out like, okay, blank percent of Brian's class likes anime, blank percent of Brian's class liked failed. What is the rule when you multiply two probabilities? The two probabilities to multiply them together must be what? If you multiply two probabilities, the rule is that they should be what of each other? Independent. Yes, exactly. The rule for multiplication rule is independent. So when you come up with these expecteds, the expecteds are what we would expect if they are independent. That's what the expected means, is like, if these are independent, I would expect this amount. And do you see how close these numbers are? My numbers here are very close, which goes back to the output. When you look at the output, do you see that there's barely any difference? What am I talking about? I'm talking about this right here. There's barely any difference. It is true that more of the students will hover over, and we'll make it appear, there it is. 51% of the students who liked anime failed, and versus a little less than 50% right here, whereas only 49.2% of the students who did not like anime failed. Now these differences are likely, I love hearing in the chat, I'm gonna say it first, these differences are likely by random chance, because they're not really that large of differences. The differences are so small between what we observed and what we expected that the differences are likely by random chance, and that's what your p-value right here is showing you, that it's probably just random chance. I mean, there was just a little bit more, and it could just be that way if they're independent. How would you know if they're not independent? P-value. Great question, Annie, right there. Amazing question. And Zach, you are right. The null is that they are independent. Now watch this. I'm sorry, anime fans in the chat. Let's pull this up right here, and let's do the following. We are going to show how it would look if they're not independent. So all of a sudden now, Brian's section gets way bigger, and we have 80 here, and then we have, let's pull it up so you can see it happening, And, oh, does it automatically recalc those? Cool. And we have 180. And the pass rate gets better. And then we have maybe 90 here. And we have 5 here. Okay. So it's very, I'm going to have to pull this, we'll have to make it bigger so it's easier to see. I want you to think about the way this graphic looks, and we can do some by just looking at it. Oh, good, 10%, like it. So now, the percent of non-anime fans who failed was 10% versus 53% of the anime fans failed. And so what do we get right here? What do you think has gone up? The chi-squared test statistic or the p-value? What has gone up? What has gone up? The chi-squared test statistic or the p-value? Which of those two would have gone up right here? Think. Reverse it. The chi-squared test statistic has gone up because there's bigger differences between what we observe and what we expect. So the chi-squared test statistic has gone way up, and these differences we are seeing are less likely by random chance. So this tells us that there's bigger deviations in the plot. This right here is a measure of how much these things deviate, and if they were completely flat, the chi-squared test statistic would be what? If they were completely flat, we can do that pretty easily by just entering in 90 a few times. If they were completely flat and there was no deviation, then the chi-squared test statistic would be what? The chi-squared test statistic would be 1. You can see it right, 0, excuse me. The p-value would be 1. I was getting ahead of myself. Because it's the deviation we're seeing, and this is no deviation because everything is exactly what we would expect when you do the calculations. There's no deviations. And then we would get a p-value of 1 because this is what's most likely given that they're independent. If they are independent, it should look like this. If they are not independent, how should it look? So this is an example of how it would look if they're independent. If they're not independent, they should look like this. This is a good example of things that are not independent because if you are in the A group, you're more likely to fail, and if you're in the NA group, you're less likely to fail. But then here, they're completely independent because both groups have a 50-50. What do we mean by independent? Your grade is or you passing and failing is independent of liking anime. Because either way, you have a what % probability. Up here, you have a what % probability right here. Either way, it's what? No matter what, it's independent. It's like, well, it doesn't matter if someone likes anime or not. Either way, they have a what % probability? 50%. And here, it's more drastically different. Here you can see that there's a bigger difference. And I will note that these differences, I'm blocking the p-value, are unlikely by random chance. That is very clear. Make sure you realize, though, and I want to point this out, I'm going to make the numbers a little bit closer. And let me ask this question here to make sure everyone gets exactly what I'm saying, because these are some of the things I see people make mistakes on the test. Oh, man. Okay, cool. You guys, if you notice, there we go, we're good. Okay. So are these differences right here likely by random chance or unlikely by random chance? And what am I asking you to consider? Do you think that these differences are likely by random chance or unlikely by random chance? You should ask me to look at something. You should say, Brian, we should look at the what for this test? And they are unlikely. You are correct. And we should definitely look at the what? The p-value. The p-value, you're right. When we're talking about if we reject the null or not reject the null and are these differences statistically significant, that is the p-value. We'll do a few other tests here coming up in a moment. And I think there was a question way back earlier. Please repeat the question. I think it was Hunter maybe asked it. But this is the p-value here telling us that the differences we observe up here are unlikely by random chance. Make sure to look at your p-value to tell you should you reject the null. On this test, I would say I reject the null. I have evidence that somebody's view on anime is not independent of them passing the class. That tells me that there's an association where people who like anime were more likely to fail the class versus those who did not like anime were less likely to fail the class. Notice how I can interpret my results for step 4, which is tell us, do you reject the null or fail to reject the null? And since my p-value is below alpha, when your p-value is low, reject the null. I reject the null and I have evidence that there is an association between liking anime and failing the class, or the two are not independent. And I'll say that association means not independent. To say something is associated, that means it's not independent. To use the independent means and when you're not for the 2 sample t-test. So and that's a great question. Let's do that right here. And I'm going to open up some Stat 201 data. So that is the chi-squared test of independence review right there. Usually we use a 0.05 alpha, 0.05 alpha unless otherwise specified. So since that p-value was below 0.05, I rejected the null. Great question from Hunter right now. He asks about the when to use the independent condition with the two-sample t-test. Here's the long answer, which won't be that long. There is such thing as called a paired t-test. Now pretend you didn't hear about the paired t-test. But in this class, we will only be doing independent means tests, and let's talk about what that means. The independence condition that we talked about earlier is when we test two means, and if we do the independent means test, which is a two-sample t-test, we assume that the two means are independent of each other. So let's analyze the GPA of males and females. If you notice here, gender and GPA, the y variable that I'm analyzing in a two-sample means test has to always be a what variable. The y variable in the two-sample means test has to always be a what variable. That y variable has to be a what variable. It has to be what? The what, you got it, it's quantitative. Nice answer right there, it is quantitative. And then if you notice, the categorical is what creates the two groups, the two means. So then you analyze, and let's run the test right here. Here's the test. We're going to bring this data over to Jump to take a look at, or over to our workbook to take a look at it. Okay, so let's grab the t-test right here and see what's going on. Okay, and let's open another new, oh, there was a two-sample t we did before. Okay, so when we do this, I love this output. Use the output to help yourself by writing nulls and alternatives. Now don't just write this one spot and then finish. If you want to write the null and alternative for this test, it's just as easy putting a mu there and a mu there and puts equals 0. Someone in the chat, if you could, write out the null and alternative. You can use a u for mu, but try writing out the null and alternative like I've written it out and see if you can do it by just putting your mu male minus mu female equals 0. That would be the null, and if you want to write the alternative, you can just change the alternative to the sign you want, like it's greater than 0, which would be this one right here if you're testing the greater than test. And that would be that males have higher GPAs than females. So make sure you can write out the null and alternative, and I often like to use the output as visual cues. As when you see this output, you can just put mu subscript male minus mu subscript female equals 0, and you've written out the null, and that's the null. And once you know the null, you know the alternative. And I want to see in the chat, the null always has the equal sign. You guys know I love you guys saying that because it's important we know exactly. Jessica, great job, great practice right there. Mean of male minus mean of female equals 0, and then just change the sign for the alternative. That's all we have to do when doing statistical notation. And if we see this output, we know what to write. And good practice to just do it right there. So it's just that there is no difference between the two means. But let's interpret a lot of this output right here, and let's look at that independence condition. So there, I like it, alternative right there. When we think about what the independence condition means, we have to think about males and females and their GPAs. So the independence condition means that the mean of males is not impacted by the mean of females. So you have to think, does the GPA of guys impact the GPA of girls, like directly? Like guys do better, and then all of a sudden girls do better because guys are doing better. And they are, and that's, yeah, you're right, they're independent of each other. One of the more classical examples is to have like version A of the test and version B of the test. And if you want to see if version A is different than version B and you give it to different students, then that would be independent means. So someone might be wondering, when would we fail this condition? Like, when do you fail it? Imagine you go to Kaplan, and Kaplan gives you a test before, and they give you a test after. So you ask yourself, would your before test on Kaplan impact your score after? Do you think someone's test on before Kaplan gives you information about their test after? Like, you know, someone went to Kaplan for ACT practice and they got like a 30 on the ACT and they want to get a higher score. Does that give you information about what they might be making after? I would think they would go up. So someone who's making a 30 before probably would be making like a 33, 34 after going to Kaplan. Whereas someone who makes a 10 going into Kaplan on the ACT might be making like a 25 or 26, who knows what they'll be making. But in this instance, I want to make this clear, that would be dependent means. Those are paired tests, which we're not doing in this class, but that would not pass the independent condition because knowing what somebody had before going to Kaplan gives you information about what they might have after. But if you were to get the GPAs of guys, that would not tell you the GPAs of females, so you wouldn't get information. Sydney, amazing answer in the chat. Sydney is 100% right, and thank you for everyone helping in the chat. We do try to make it clear in the question. We say like, is there evidence of a difference between the GPAs of males and females? Is there evidence that females have higher GPAs than males? So if we ask, is there evidence that females have higher GPAs than males? You can actually take, and here's a trick I like to do, take this less than and put it between, and it's that males have less than females' GPAs. So you can actually just take that sign right there for practice, and just to make sure you put it the right way, this sign right here would go between and be males greater than females. Is there evidence that males have higher GPAs than females? Depending on what the problems, yes, you guys are, man, love seeing these answers in the chat. Thank you, Julio. It's amazing answers. But you can kind of use that as a cheat. Knowing the output is really good for the test. Two-sampled t-test is really good output to understand, and that's why we're looking at it right here. So we have written out the null and the alternative. What does this difference mean here? Let's interpret this difference in context of the problem. This difference right here is actually that difference right there is the difference between the sample means, and I guess we could make it clearer for this question, that this difference right here is the difference between the sample means, and so it's the difference between the mean of males minus the mean of females. Since the difference is negative, which of the two numbers was bigger? Since the difference is negative, we know that females had a higher sample mean. Since the difference is negative, females had a higher sample mean. So the mean for females in the sample was 0.24, 0.25 basically, points higher than the mean for the GPA of males. Does that make sense to everybody right there? I'm going to do some really big stuff right here right now, because here's some of the big confusion I see. There are two formulas for this, and we're going to do both formulas right here. So let's do both formulas. We have the test formula, which is y bar 1 minus y bar 2 over, excuse me, guys. There we go. And now we get the t right here with degrees of freedom. Next, we get the confidence interval. Brain's breaking right there, go. Y bar 1 minus y bar 2 not equals. Plus or minus the t statistic. And we put a star, meaning we get to pick that one. And then we do square root s sub 1 squared over n sub 1 plus s sub 2 squared over n sub 2. Oh yes, definitely. Hunter, great question. We will make that alternative super clear on the test. We'll make it as clear as possible. Some of the homeworks are not super easy to understand, and you are free to ask us, and we'll be like, oh yes, it's saying that you should see if there's a difference. If it's saying you should see if there's a difference, which of these three alternatives should you use? The first, the second, or the third? If you want to see if there's a difference, which of those would be the right p-value? If you want to, we'll do that one next there. Keaton, I remember you asking that earlier. We'll do your question next there. The first, Zachary, you are right, because this is the does not equals, this is the greater than, and this is the less than. So really good practice right there. Really good to understand which p-value to take. If it says we should see if there's a difference, then the alternative would be does not equals. I want to point out that this right here, this difference right here is this value. Does everybody see that? And then we have right here, I'm going to circle in the green box. I'm going to put a 2 on this for using red-green, not a good idea. So the value in box 1, is the value in box 1 right there. The value in box 2 is the standard error. So if you're seeing 2 right there, then that's the standard error. So if you think about this, we can actually solve this. Like, can anyone do in their head what is negative 0.24 divided by 0.03? Like if you take those two numbers and divide them, what would you get? Just think. That's the t for the test. That is the formula right there. So this value right here, this t for the test, is that value. I'm going to erase some stuff up here. That t for the test right there is that t. But I want to make this very, very clear. that t right there is not, I don't know how to make this more clear, but this t, let's put this right here, not the same. Those t's are not the same. Those t's are not the same. There's a good practice test question on it. That t that I'm pointing at is not the same t. The t with the star is one you pick, and it's based on your level of confidence. So the t with the star is based on a confidence level, and it's actually related to what's going on down, and let's show where it's at. It's related to the value down here. That's what that star means right there. That star is related to the level of confidence, so if you change it, it'll change what the t is that makes the interval. Now here's a classic trick, and it kind of works for the practice test, but the t is often equal to 2 because it's very close to a 95% confidence interval. Now I'm not saying it will be 2, but the sample size here is so large that it's basically the z-score, which is 1.96 or basically 2. So you can take, and let's show this. If you were to take and try to figure out what the t is, we need to do, and this is a practice test question, so it's a decent one to do. We're going to say that we want to find out the t-score that was used to make the margin of error. So the lower of the interval, this value right here, would be found via the formula, which I had written up there. It would be the t-score times, it would be the difference minus the t-score times the standard error of y bar 1 minus y bar 2. I can solve this to find the t-score because I'm just missing one thing. Great question, Annie. I'll answer that in 2 seconds because that's a tricky one. And so now negative 0.29335 is equal to the difference up there, negative 0.24754 minus the t-score, and then we have the standard error of 0.02335. So all we're trying to do now is solve for the t. And I'm going to do a good review of that next, Annie, and then we're going to do the question du jour. And so let's take the 0, and we're going to subtract from that, so that's going to be interesting. I think I'm doing all the math right in my head. Let's do negative. How do you do negative on the calculator? Is that negative? 0.29335 negative, good. Subtract from that 0.24, oh no, we're going to add, well, it has to be added because we're going to add up, we're going to do the algebra. So actually, it'll be positive then. So let's do it. 0.29335, and then we're going to add to it 0.24754, and that, I'm going to write that down here. I need to see it on the screen though. Negative 0.4581, negative 0.4581 equals to t with times this right here. So now all we're going to do to find t is divide it by that, divide the first number, divide 0.02335, and we should get about 2, and we do, or even super close to 1.96, which is what I said it should be close to. So the t that was used to calculate this, that's what t is equal to. So t is equal to 1.962, and it's plus or minus that right there. Then we're going to do some degrees of freedom, but that is a practice test question right there. And I'm basically, if you're wondering where I got this formula from, it is from this formula right here. I'm just using the lower of it by doing the minus alone. Does that make sense? Why leave the negative out for the t? Because the t is plus or minus. Great question right there. The t is plus or minus. So I just solved for the lower, and then the upper would be positive. So the t that was used was plus or minus that t, and I just solved for one side of the equation. If I had solved for the positive side, it would have been, or the upper side, it would have been positive. Great question, Hunter. That's why there's so much stress on how to interpret this. Oh, let's see, have jump screenshots. Yeah, there's a lot of jump screenshots. And then let's do degrees of freedom. Let's make a degrees of freedom table here. So here are the degrees of freedom notes you should know. Let's talk about degrees of freedom. There are 3 times that we use degrees of freedom in this class. So the 3 times we use degrees of freedom are going to be, let's go here with one sample mean, one sample t, and chi-square. So for the one sample t, I love this one. What are the degrees of freedom for a one sample t? What are the degrees of freedom for a one sample t? Any crazy ideas out there for the degrees of freedom for a one sample t? When we do the degrees of freedom equals, well, what is it? They equal 1? They don't equal 1? No? What are the degrees of freedom for a one sample t? Oh, I'll say it since we got limited time today. N minus 1. Yes, there we go, N minus 1. The degrees of freedom for a one sample t are N minus 1. So you have to take your sample size minus 1 for the degrees of freedom. Now what does this tell you? What do the degrees of freedom tell you? What are the points? What is the point of degrees of freedom? Well, let's bring up some very important stuff right here and see this. All right, we are going to look at what do degrees of freedom tell us and why do we need degrees of freedom. So the degrees of freedom are going to tell us what distribution we are using. So if you look at this right here, in my problem, I might have a sample size of 110, then what are my degrees of freedom? If I have a sample size for a one sample t with 110 as my sample size, what are my degrees of freedom? If for a one sample t and a sample size of 110, my degrees of freedom would be, what do we got in the chat? 109, you are right. If you notice, do you see how the curve changes when I change the degrees of freedom? When you change the degrees of freedom, the curve changes and the numbers change. So you have to calculate the degrees of freedom to know what t-curve to use. The wrong degrees of freedom gives you the wrong t-curve. No, they are on the formula sheet. Audrey, ask all the questions. The degrees of freedom calculations are on the formula sheet except for one of them, which we will not have you do. I showed it in one of the things. So 2 sample degrees of freedom. So the formula for the 2 sample degrees of freedom is not on the test and we will not expect you to do it. Let's copy this image. Let's go back here to Word, our 10,000 documents. So there we are, we're back on the screen. Cool. So the 2 sample t degrees of freedom. There we go. Look, oh, we need to move it behind. I'm not writing this one out. Can't make me do it. I bet I can memorize that. There's no point. I've never solved that one by hand, but that's the degrees of freedom for that one right there. You are not going to work that one out. We would just give it to you. If you notice, it's based on standard deviations and it's based on sample sizes. It looks a lot like the standard error, so that's why it's pretty interesting and it repeats on the bottom. Now I kind of want to memorize it, but you will not solve that. Let's put it like a no on that, like no, we're not making you solve that. That is found via the applets. If you've gone and done a lot of your assignments, you know that we just put it into an applet and we just let it solve the answer for us. So let's put a note on it, solve with applet. So that's really the test questions we've written in the past have been like, the 2 sample t's degrees of freedom are n minus 2, and that's false. Or the 2 sample t degrees of freedom is a complicated formula, that's true. And complicated is subjective, but it's not as easy as n minus 1. So this is the 2 sample t degrees of freedom for independent samples. It's complicated. You will solve that with an applet. Now, one of my favorite ones to do is the chi-squared independence degrees of freedom, because it's going to be rows minus 1 times columns minus 1. So let's make this as clear as possible. So we can do better than that. I have to write big so even I can read it. So let's go here and go to rows minus 1 times cols minus 1. This is an easy formula to do. Like, I know it's like, oh, it's easy, but it is, I promise. Let's go back to our first question we did and see if we can figure out the degrees of freedom. I ask my students to say this out loud. Brian, that's a what by what graphic. Brian, that is a blank by blank. I want to hear it in the chat. I want to see it. I want you to be like, Brian, that is a blank by blank. Brian, that is a blank by blank. Oh, you already figured out the answer? No, you got the answer to it. Brian, that is a 2 by 2. So since it's a 2 by 2, we're going to move it over here so we can see how to do it too. Brian, that is a 2 by 2. We're doing the chi-squared. 2 by 2. So now we drop it and we get 1 times 1. 1 times 1 is 1. You can also do it a lot of other ways, but remember, and there's the degrees of freedom shown to us in the output, but since it was a 2 by 2, do not count the totals. Nice job in the chat. Do you use a chi-squared test with expected or what is given? You use the observed and the expecteds to figure out the cell chi-squareds, and from the cell chi-squareds you get the test chi-squared. From the test chi-squared you get the p-value. From the p-value you reject or fail to reject the null. Great reviews on that, and definitely check out the start and keep asking those questions if I don't make something clear enough. But does this help maybe help you better understand where you're using degrees of freedom? And remember, you should know when I say one sample t, that's when you're testing like the average GPA of students. When I say two sample t, you're testing like the GPAs of UT students versus Florida students. The p-value calculation will most likely be given to you, but you bring up an amazing question, Annie. Let's do something right here. I want to do a question that I thought of would be really helpful. I want to look at one of the applets. So let's go to the applet right here, and let's take a look. Okay. And here we are. Imagine you wanted to make a confidence interval. Which of these buttons would you press to make a confidence interval? Would you press the first, the second? Actually, you know what? We can draw on this. Let me screenshot it. I'll blank that out when I screenshot it. Okay, we're going to do it as drawings because it'll be easier. Got the nice tablets, so let's do that. And let's bring it into Word. Open up another document, drop it in. Cool. Okay. You are right, the middle, the one, not the one that's in the middle, but the one that has middle on it. Yes, that is the one you would use. And so we're going to draw a little. Great answers in the chat. Little fake button right there, radio button. There we go. Now it looks too. There we go. Oh, yeah, good. It's, yeah. Or wait. I bet if I. Okay, looks almost right. So what you would use, this right here is really your best for confidence intervals. This is your less than test. This is your greater than test. And this is your does not equals test. So you can use them for other things. Like if you wanted to make a 95% confidence interval, what could you do with this right here? Let's highlight this. If you wanted to make a 95% confidence interval, what percent could you put in there to make a 95% confidence interval? Like what would I put in here for my probability to make a 95% confidence interval using that one right there? I'd put 1 in to make a 95% confidence interval. I want to make a 95% confidence interval, and I click this button right here. So what would I put in? You got it. You'd put in 0.05. And that would make a 90. You could use then the values from this to make a 95% confidence interval. How are we going to use an applet for the degrees of freedom on the two sample t? Oh, we won't. Hunter, great question. We can only really ask theory questions on that. We don't expect you to solve stuff like that. Amazing question. We would maybe just say like the two sample t has a degrees of freedom formula of n-2, and the answer is no, it doesn't. It's a complicated formula. So we would not expect you to know very, very complicated stuff on that. Just generalities of that it's a complicated formula, and that also the degrees of freedom tell you which t distribution to use. Like in the previous problem, I was talking about degrees of freedom of 109. Oops, that's the wrong spot. I was like, no, it doesn't go in the t. 109 would go into the degrees of freedom. That's if I'm doing a one sample t with a sample size of 110, we would have degrees of freedom 109 because the degrees of freedom are n-1. Can you explain the two-tailed thing again? Is that just the two sample t? Great question, Annie, in the chat. The two sample t is different than the two-tailed test. So when we look at the tails of a test, I'm going to draw out here 3 tests. We got test 1, test 2, test 3. And we're going to land right over here. We're going to land, I'm going to put a line down like that. So we have the tails of a test are decided by the sign of the test. Take that note right there. The tails of the test, I'm going to do an orange jump, I think. Whoops. The tails of the tests are decided by the sign of the test. The tails of the tests are decided by the sign of the test. So we'll start off here with the easiest one, the greater than test. We shade greater than it. Well then, if we shade greater than for the one, and this is called a one-tailed test, let's put that over here, one tail and two tail. So the one-tailed tests are the greater than and the less than test. Let's do a little math right here. If this is equal to 16%, then what is this test equal to? What is the p-value of the other one? And maybe we'll do it as a p-value instead. What is the p-value of the other one? See if you can solve that. Sorry about that. I don't know why it likes doing that to me. It likes bringing it up. I shouldn't have done that. I should have just erased normally. So what? Oh, wow. Okay, there. We're perfect. Don't touch it. What does C? Oh, I'll go back to that in one moment here, Caroline. Great question. Stands for confidence rule. I should just say that. I was writing confidence rule. If this is equal to 16%, then what is, Zachary, thank you in the chat. If this is equal to 16%, what is the less than p-value going to be? 84, you are exactly right. And then the two-tailed test is called two-tailed because we take and we reflect, and that's a bad reflection right there. I don't want to do that. Sure. It might not look accurate. I'm sorry if this doesn't look accurate. My curves might not be perfectly drawn to scale, but this one would be what percent of the area right here. If this is a reflection of it, which it's meant to be, what should it be right here? It doesn't look perfect. I'm sorry about that. It should be total area on outside the curve right now. The total area outside the curve should be what? And this is because the two-tailed test is always double the smallest. So the outside area should be total 0.32. So the total area outside is 0.32. Nice job, answers in the chat. And if you notice how the p-values work, the two-tailed is just a reflection of the other side. And I meant to draw those out perfectly, but I didn't. But we can see here in the output what we get, stuff like that. It was two more back. Yes, that one is so far gone. I'll make an output where it's easier to see. Let me make one of these right here. Let's go to Analyze Distribution. This will be a one-sample t-test. We'll test the age of 201 students. That is really skewed, but I don't know. That one's a tough one to tell if the nearly normal's met because the sample size is ridiculous, but the skew is ridiculous. So let's not do that one. Let's do GPA. I would not like that as a test question, so I'm not going to do it. And here we go right here. That this would meet the nearly normal condition. It does have outliers, but the sample size is very large. What would you need the two-tailed test for? Great question, Annie, and we're going to do that right here. I want you to tell me, is this a one-tailed or two-tailed test, and how do you know? UT wants to see if the GPA of students is less than 3.8. UT wants to see if the GPA of students is less than 3.8. Is that a one-tailed or two-tailed test? So let's identify here, is it a one-tailed test or a two-tailed test? UT wants to see, and you got it, we want to see if it's less than. And going from our notes from just a second ago, we can see that the less than test is a one-tailed test. It just shades one side of it. The two-tailed test would be UT wants to see if the GPAs are different than 3.8 or wants to see if they are or are not 3.8. So the less than test is a one-tailed test, like the greater than test is a one-tailed test. So now that we have this output right here, we can actually test it. I chose one I could kind of do in my head. I think the p-value is going to be about 0.025 or 0.023. I say it's going to be 0.023. Let's see how close I am. Is it 0.023? Is it going to be 0.023? Am I doing it correctly? No, I did it way wrong. It's going to be ridiculous. Oh no, 0.0023. I just forgot an 00. Close-ish. And that is the less than test right here. I'm going to choose one a little bit closer to it now. And I can explain what I'm doing right here, but let's see a better p-value, and I'll show you why I want to look at that. 3.78 going. That'll really reject the null. Okay, good. Let's look at this output right here, which is very important, and see what's going on. Excellent, I love this output. We're going to copy this output and bring it over so we can examine it more closely and know what's going on with these graphics. Okay, so what you notice right here is that just like I was drawing out earlier, we have the red line, which is our result. This is your y bar. That was your observed sample mean. This value of 3.78 is mu naught. That is the hypothesized mean I put into the box. So 3.78 is my hypothesized mean, and the value of 3.76 something is my observed mean, my sample mean. So I put y bar right there. And I put a sharper red line so you could better see what's going on. Now this dark blue area is what percent of the curve? This dark blue area is what percent of the curve right there? You can round it to just 2 decimals or round it to just a percent. That dark blue area is basically what percent of the curve. Careful. Previous problem we had it be something like that. In this problem, that dark blue area, think about this. You want to take, and I'll show you how it works with this output. If you look at what's right here, here is the less than, which means on that one, you shade below it. So it should be up. This one area right here is exactly this right here. It is 12.04% or point, yep. And so that means if I were to reflect that on the other side, if I were to reflect that over here, and I went through it, but if I were to reflect that on the other side, then what percent of the area would be if I reflect 12% on this side and 12% here, making it a two-tailed test? I'd have what? Great answers in the chat. If I reflect it, I then get, you can see it, the two-tailed test, which is this one. That is the does not equals alternative. This is the does not equals, this is the greater than, this is the less than alternative. Important to know which alternatives you're looking at right there. But how about the greater than alternative? The greater than alternative is not really shaded in on this output. To do the greater than alternative, I would need to shade here. So to do the greater than alternative, it would, and I'm going to make it look really nice, the greater than alternative would be this area under the curve. So what is the area under the curve for the greater than alternative? The greater than alternative has what area under the curve? Oh, I think people are getting it. I like seeing that. The greater than alternative is 88% of the curve. Exactly, Zach, you're doing the answers in the chat. And we're just going to round it nice and neat. This is 12%, and then this is 88%. And if you notice, that's where these numbers are coming from up here, because all you're doing is going above or below the points. You're going above or below. Is that maybe making more sense with this output? And here's the thing. Can you reject the null for any of these? You wouldn't just pick from these randomly and be like, oh, I'm just going to look through all the p-values. That's bad statistics. But just understanding, we should know that all these p-values are above 0.05, and we would fail to reject the null for every single one of these p-values right here. Does that make more sense to everybody with this output and how we can get p-values from this output? You can also see the test statistic is not that large of a t-score. It's only a t-score of negative 1.17, which is not that large of a t-score. More questions. How would we be able to find the t-score if it was not given? Great question. Let's look at that output and do that question. We have not done a one sample t-test today, so let's do it. And let's grab the output. This output right here, I'll grab all this. Let's try to label our output and make sure we know how to label everything. And in one of my previous videos, what's the saying again for rejecting the null? I reject the null, and then say what you're doing. I reject the null that students' GPAs is equal to this. I have evidence. So the key phrases are, I reject the null, then talk about what you're rejecting, and then say, I have evidence for the alternative that. When you fail to reject the null, I fail to reject the null, I do not have evidence. So I reject the null, I do have evidence for the alternative. I reject the null, I do not have evidence for the alternative. Great question in the chat right there. So those are key phrases we like to use to make sure we say it correctly every time. Next, let's go right here and let's take and do some notation. I see right here that this is the what mean. I'm looking at this area over here. We're going to go down and interpret all of those right there. What do we have as that first thing? I want to see it in the chat. I want to see some notation. What kind of mean is that in the output? What kind of mean is that? Anyone know what kind of mean that is? It's just a mean. Is it just a mean? That mean right there is, in notation, It is y bar. In a question, it could say, and that'd be the sample mean, it could say, we went out and spoke to 1,308 students. And in those 1,308 students, we observed a sample mean of 3.765, yada, yada, all the numbers. And so that is a sample mean. Next, we have a sample standard deviation. And if you're wondering how I know these are from a sample, remember, population parameters, sample, statistics. And these are the observed. That is true too. This is what we observed in a sample, so we can use it that way with like z-scores and t-scores, which we'll do t-scores here in 1 second. So now that we have, oh, this is awesome. So now this is the standard error of y bar right there. And then we have a confidence interval already, so we've got our 95% confidence interval. Does anyone know what the hypothesized value of the mean is? The hypothesized value of the mean is what in notation? And I want to point this out. It is mu naught. Naught is the value that goes with the null, such as when you write a null hypothesis, you usually write mu equals mu naught. So whatever value you're putting, if it's like 3.8, you'd be putting that right here. If you're doing a test on the proportion, you'd simply write the null as p equals p naught. And that p naught is the value you are hypothesizing it is true. So does everyone see that little o right there? That just means the hypothesized true value. So when we say we're hypothesizing that 3.78 is true, that makes it mu naught. I'm saying I believe that the true mean is equal to some hypothesized value. And make sure to just read that off. I believe that the true mean is equal to some hypothesized value. The null states that the true mean is equal to some hypothesized value. So we have all the notation pretty much that we need. If you notice here, it does give you, once again, on this side of the screen, it does give you y bar over here. That is y bar, that is mu naught. And degrees of freedom, that is the df, which is n minus 1. Standard deviation, that's just s again. So we have a lot of the same output. And now let's figure out how we could do the t interval or the t test. What I want to point out right here is this t test, once again, that is not the t for the confidence interval. So let's go ahead and find the t for the confidence interval. You ready for this? What we have to do, which we could have you do on the test, and let's use the applets we have, which could be on the test, is you'd have to go here and enter in the degrees of freedom as 1307. There were 1,308 observations, so there's 1307 degrees of freedom. We need to then go and enter in the probability of a 95% confidence interval, choose the middle option, and choose the value, 1.962. Now I could have selected it this way, which we talked about earlier, and now we could choose and we'll get the same value. I can delete it and show same value. It's because if there's 5% outside, there would be 95% inside. It's just inside outside of the interval, and you'll still get the same value right here, and that is the value for the t statistic for a 95% confidence interval. This t has now been solved for, and we're going to use it here to make our confidence interval. So let's go and take a look at this right here. We have y bar, which will be given to you on the test, plus t star. That t star means it is based on the confidence level, so this 95% is how we're picking the t. Then we do s over square root of n. Very important stuff right there, so we know what's going on. That t we found was 1.9, and so we'll put t in the output right here. Let's put t star, because this is not the test statistic t. This is the critical value used to make a confidence interval, is 1.962. We can show you pictures on the test to help you figure out that mu and y hat on the jump output. Great question, Carolyn. So y, and it'd be y bar. Y hat is the predicted value from a regression, where y hat is the predicted value from a regression. Y bar is the sample mean. So in a test question, it would say something like, from the 1,308 students, we found a mean of this. So that is the mean from the sample of students, but then it would say, see if there is evidence that their mean is lower than this. So if we said, see if there is evidence that their mean is lower than this, that makes the hypothesized value the value we are testing. The hypothesized value can be anything you want. And so great question right there, Hunter. We can show you pictures. We like taking screenshots and being like, which of these pictures would you use? So it's basically like you have access to it, and we're just limiting like which of these pictures would help you out. So we've done that on a lot of tests, like show you like here's applet pictures, use like the proper applet to figure out the right answers. Does that help make sense? The confidence level numbers will be given right. I think, yep, I think that's yes. I think I know what you mean by that. We will give you the critical values. We will often say like, here's the t, or we will show you pictures and be like, here's the, use pictures to help you solve for which t. So as long as you know, if you knew, put it this way, If you knew how to enter in the numbers here, that this is like 95% in the middle, here's your degrees of freedom, which is found by n minus 1, then you'll be good. Like if you could have done this, then if we put a picture that shows you should be like, oh, that's the picture because it has the right degrees of freedom, it has the right probability, and it's making a confidence interval. So if you could do that, it could definitely, I'm not saying it is, but it could definitely be screenshots. We've done that a lot in the past. I'm not saying it is, but highly likely. So with this right here, let's see and solve our interval. We take 3.7659 plus or minus, and then we do 1.962. The degrees of freedom of the n minus 1, you don't write that out. It's just subscript that is telling you which t to be using. And then we go here s over square root of n. But you know what I'm going to do? I'll do it seriously. S over square root of n. If you solve this, if you were to solve this interval right here, you would get both these answers right here. If you only solve this portion right here, what will you find? If you only solve that portion right there, what would you find? What I have in the blue box would solve out for the what of the interval. Everything in the blue box right there. The margin of error. Great job. Hopefully you guys are having some fun. I really need like a Red Bull refrigerator so I can just like open up and grab my Red Bull. That would be the margin of error. That would be the margin of error. The standard error is, here, let's put it right here. This whole thing, this is the t, and this is the standard error. That whole thing is the standard error, and altogether, it makes up the margin of error. Everything in the box is the margin of error. The last part, the s over square root of n, is the standard error, and the whole thing is the margin of error. So does that make sense? You literally have your t and your standard error, and it's very similar to other formulas. Just so you can see the similarities between formulas. Y bar 1 minus y bar 2, and then we do plus or minus t with degrees of freedom. And then if you go here, well, I was going to write out. Let me write out. Stop doing that word. S1 squared over N1 squared, not N1 squared. It's like I know what to do, and I don't know what to say. And this right here would be the t, and this is the standard error, and that makes up the margin of error. So that's the two confidence intervals on the test. So when do you use that equation to find what? This is to build a 90, this equation up top is one sample t. So this is one sample t interval. And the only difference here is two sample t interval. And if you notice why it's two sample because of that, and that's why it's one sample. So what we mean when we say one sample is we're saying how many means are we looking at. So that's how many means we are looking at when we're doing the test right here. There's two means, there's two samples we're looking at, and that comes to the rule of independence, that we want the means to be independent means of each other. So that is what we're analyzing, and that is our best guess of the difference between them. I think that answers the questions. Oh, there was something else I was going to say. One sample interval questions would be things like, let's figure out what the GPA of UT students is. Build a 95% confidence interval to figure out the GPA of UT students. Two sample means questions would be things like, let's look at the difference between the GPAs of UT students and Florida students, and of course we're doing way better, but let's see what the difference is. So if you look at this right here, would be the sample difference between the two means. That would be the sample difference between the two means, and then we'd get a margin of error, and we'd analyze it that way. Additional questions, let's go for another 30, 40 minutes. I think we didn't do the one on the practice thing, right? People wanted that earlier. Now that we're getting near the end, and I've covered a lot of topics. Woo, all those topics. We did interval stuff. The rat question, oh, it's the maze question. I think, oh yeah, type 1 and type 2, we should do that. I think, Hunter, you might have been asking about the rat question, and I think I did that one in a previous video. Any of my students here, can they confirm that I did the rat question? It's where you have to remove, so I think that's in a video, which you guys should have access to. You have to remove the outlier. Double check the video. Sorry, I just realized that I do remember the rat question. It's about them running the maze and running it less than a minute. The answer is they run it less than a minute. It doesn't take longer than a minute, or it's not in the interval. And yeah, We'll do type 1, type 2 error, but I think that's the question you had, and I'm pretty sure it's in a video. So if you can't find it, email me, and I'll send you the video, so that way you can watch it. And I have worked that problem and hopefully shown how it works. Yeah, I do too. Yeah, so I think it's in there. Type 1 is rejecting the null when it is true, and type 2 is us failing to reject the null when it's false. Jessica, great job. So ready? Let's do our practice right here. We got a cheat sheet with our hands. When you have a type 1, does everyone see this 1 right here? Type 1, the null is what? What am I making with my hands right now? Type 1, the null is what? In a type 1, the null is what? In a type 1, the null is what? We'll do some practice here with this. In a type 1, the null is what? What am I making? What symbol am I making with my hand? In type 1, the null is true. And if the null is true, what would be a bad idea? If in a type 1, the null is true, it'd be a bad idea to what it? If the null is true, it'd be a bad idea to what it? It'd be a bad idea to reject it. In a type 2, do you see the 2? In a type 2, the null is what? And think, I'm making an F right here. In a type 2, the null is what? In a type 2, the null is what? This is an F. In a type 2, the null is false. And then you say a second F, and we fail to reject it. So practice with me and make sure you say it in your head. Say it out loud. I can't tell you guys the power of saying things out loud, like Q, straight enough, no outliers, pot doesn't think, and forget that for now. But in a type 1, the null is true, and we reject it. In a type 2, the null is false, and we fail to reject it. You say it twice, you say 2 Fs. You don't say it twice, but you say 2 Fs. In a type 1, the null is true, and we reject it. In a type 2, the null is false, and we fail to reject it. You got your 2 Fs in a type 2. So let's look at some examples right here. What should we do? We should do a new one. Oh, man. So my brother and I are going to go out and play some football. And we're going to see who is a better quarterback, my brother or I. So, you know, we're like 6'3", just like, we're like average sized dudes or whatever. So no one's expecting much from us. More of the story here in a moment. So the null hypothesis would basically be what between Brian and Aaron? Same skill. Whoa, change of color. Imagine if you said someone was better at football than someone else. You wouldn't just say that without evidence. So what is the null? The null is that if you have 2 players, they're the exact same. Like, well, until I have evidence, they're the same. So the alternative would be that they have a different skill level. So I want us to think about what a type 1 error is. So imagine a type 1 error. I want you to look at the null. Here's what you do when you do a type 1. If you've written out your null, you look at that null and you say that null is true. You say it is true that both players have the same skill level. But what are you going to do? In a type 1, it is true that both players have the same skill level. Look at it. Say that it's true. The null is true. It is true that both players have the same skill level. But we conclude what? What do we conclude? We say that we have evidence that what? In a type 1, it is true that both players have the same skill level. But we conclude that we have evidence that they are different. Now, what could this do, especially if you talk about like baseball or something? If you have 2 players, like you have player A and player B, and you're trying to figure out which player to draft right here, and you're like, okay, we got to pick a player, so we need evidence that the players have different skill levels. In a type 1, you might say, okay, player B is actually better. There's a difference, and player B is better, and you might pay them more, but in truth, the players have the same skill level. So you're saying that there's a better player when there's actually not. So we could end up drafting someone or paying more for someone because we think they're better, but they're really not. So we have evidence when we shouldn't. In a type 2, the null is false. So what would a type 2 error be? The null is false. It is false that these players have the same skill level, but what are we going to do in a type 2? Since it's false that the players have the same skill level, but we are going to what that in a type 2? We are going to what it? We are going to fail to reject it in a type 2. So if you think about this in kind of baseball sense, we would think that the players have the same skill level when that is false. So we would think that the players have the same skill level, but in truth, one of them is better. The truth is that they have different skill levels, and we might not draft someone who's actually better because we're like, they're the same. They're the same skill level. But in truth, one of them is better. So remember, look at it and say, in a type 2, it is false that the players have the same skill level. So one of them is better. But we're going to fail to reject this. We're not going to find the evidence that they have different skill levels. So we'd miss out on drafting someone who has a better skill level. So you might say, well, what's worse? Type 2, we miss out on players by not finding the better skill level players. Type 1, we maybe draft someone because we think they're better when they're actually not. So you have to be able to be very careful with these. They're super easy to mix up, but review that. Let's do a super easy one of my favorite ones, because it works well with medicine, and hopefully I'm getting better. Tani. Okay, the null. When you go to the doctor, does the doctor look at you and say, you're sick, I don't need to run any tests? That's horrible. Bad doctors in the world right there. The null for doctors would be healthy. The alternative for doctors would be sick. They need evidence of sickness before they conclude any sort of sickness you have. So I like to say that a type 1 can often be considered as a false positive, because what does it mean when you get a false positive on a test? When you get a false positive, and it's just the way you think about it, because you can flip it and make it different. Like if you're sick, then a false positive might be that you're healthy. Like, oh, we found evidence you're healthy, but it's not. Just depends on where you're at. If you flip the nulls and alternatives for different people. But with this classic way of writing it, with null being healthy and looking for evidence of sickness, what would a type 1 error be? Type it in the chat. Can you tell me what a type 1 error would be? And please use the method right here of looking at the null and saying, in a type 1, the null is true. So I want you to look at that and be like, it is true that I am, but they're gonna, I want you to practice it. I want you to say it. I want you to be like, it is true that I am what? I want to see it in the chat. Who can tell me what a type 1 error is right here? What is a type 1 error which could be considered a false positive in the medical industry? Any ideas? If the medical industry said, we made a false positive on that test, what would they be saying to you? Type 1, it is true that I am healthy, but we reject it. That is correct. So if you reject that you are healthy, it is true that you are healthy, but you reject that you are healthy. It is true that the patient is heavy, but they are diagnosed as sick. Nice job, Sam, that right there. It is, you look at that. The null is true. In a type 1, the null is true. It is true that you are healthy, but we are going to reject that and find evidence that you are sick. It is true that we are healthy, but we include there's evidence that we are sick. There we go. And so it's not that you're sick, it's that they made a false positive. It's a mistake. They're like, oh, you're sick, but you're not. And think about, would people, maybe they, maybe there's just allergies and flu, right? Not flu. Maybe it's just allergies and the weather, making me a little bit congested. And so if I went to the doctor and they made a type 1 error, they might give me medicine for things I don't need. What's the impact of a type 1 error? It'd be them giving me medicine when I shouldn't take it. And would that be bad? I mean, it ups the viral or the antibiotic resistance of our society if we just keep giving out antibiotics. So it's probably a bad idea to give people medicine who don't need it. But what might be worse, especially for a lot of things, is a type 2 error. In a type 2 error, I want you to look at the null and be like, okay, in a type 2 error, the null is false. I want you to look at that and say, that is false. The doctors say you are healthy when you are sick. That is correct, Sydney. In a type 2 error, you look at that null right there and you say, in a type 2, the null is false. It is false that I am healthy, but I'm going to fail to reject that. So I am not healthy. It is false that I'm healthy. I'm actually sick, but I am going to fail to reject the null, which means I continue to believe it. If you're wondering what fail to reject means, it's an old way of saying I do not reject that. So I don't reject that I'm healthy. I guess I still believe I'm healthy. So you would still believe you are healthy. You don't accept it. You still believe it. And you would be wrong. The null is false. You are sick, but you still believe you are healthy. That would be a type 2 error. I like to do other classical things. Let's look at this right here. What about other examples? Let's do this right here. Okay, let's say buy stocks. So don't buy. So your friend loves to give you stock tips. It's always giving you stock tips. And so the null is to be safe. I'll just say that right there. The null is to be safe and don't buy stocks unless you have good reason to. You shouldn't just go invest money. So maybe there's an investment he's asking you to buy into. Crazy friend, Barney Rubble, old references right there. Get rich quick schemes. We're going like 50s references. But Show my age. And so we have right here, the null is that you do not buy, and the alternative is that you buy. Can you tell me a type 1, type 2 error in context here? Remember the trick. Remember our trick. We look at the null and we say in a type 1, the null is true. Look at that null and say in a type 1, that null is true. In a type 1, the null is true. In a type 1, the null is true. It is true that I should not buy those stocks. It is true that I should not buy those stocks. This is your chance to practice type 1, type 2 error and tell me what it means and which one is worse. I want to say this, it's not always that a type 1 or a type 2 is worse. It all depends on the situation. You have to analyze and think about, is it worse to make a type 1 or type 2 error? And a lot of statistical models try to balance or figure out the ratio of type 1, type 2 errors they want based on a cost-benefit analysis on which is kind of cost more. So what is that type 1 error? Remember to use your trick, look at that and be like, that is true. I should not buy those stocks. Who's got it in the chat? Remember, be practicing these, be writing these down. So I think I might say it here. In a type 1, the null is true. So I should not buy those stocks. But I'm going to reject that and buy the stocks. So a type 1 error would be when it leads to a bad investment. A type 1 error is probably someone who makes a bad investment because it is true. Stocks should not be bought, but I buy them. Sam, great answer right there. You're right. So it is true that the stocks should not be bought, but you reject that and you buy the stocks. So the type 2 is just the reverse of that. Look at that right there again and say, don't buy the stocks, but reject anyways and buy them. Yep. So it's someone who buys stocks when they shouldn't. Type 2, I should buy the stocks, but I don't. Yes. In a type 2, the null is false. And it's weird to say it is false that I should not buy them. So you should buy them. It is false that you should not buy them. So you should buy them. But you fail to reject the null. I still believe this. I still believe I should not buy them. So tell me what a type 2 would be. A type 2 would be missing out on an opportunity because the null is false. You should buy them. So in a type 2, you miss out on the money you could have made by buying the stocks. So in a type 2, the null is false and you fail to reject it. So you miss out on money you could have made by buying the stocks. Now, the type 1 error is alpha. A type 1 error is alpha. Let's do back in time. Oh, that's it. That's all we can do. A type 1 error is alpha, and a type 2 error is beta. So you remember alpha, beta, 1, 2. There are 3 things that impact beta. The 3 things that impact beta are sample size, alpha, and effect size. I mention the instances with my brother because if you were to watch my brother and I play football for maybe a minute or an hour, which of those would it be easier to reject the null on? It'd be easier to reject the null if you watched just for an hour. If I were to play my brother or Tom Brady in football, who would be easier to see who's better? It'd be easier to see Tom Brady's better, and that's because of the effect size. There's a larger effect size between Tom Brady and myself, and then between my brother and myself. And Tom Brady was like, if you heard me say 6'3" or whatever, Tom Brady's like, it's like basically the same size as me, at least when he's going to the NFL. And everyone's like, yeah, that dude's not going to make it in the NFL. Like, I'd never make it in the NFL. But it turned out to be one of the top quarterbacks of all time. It's going to get ring number 7 here. It's going to happen. Will we have to answer a question similar to the homework where it asks which error is worse? Yeah, you could. And then you have to, it's tough. We try to make those ones as clear as possible. We oftentimes have questions that kind of relate to like, what would the error be in this context? You know, what does this mean for the person who would encounter this error? Great question right there, Ryan. We try to be like, what is the context of this error and which would be worse? But those are the 3 things that affect, and let's write right here. Power equals 1 minus beta. Let's try to cover at least one more topic. What other topic do we have that we haven't discussed lately? I feel like we did like, do you guys feel like we did, who's still here? How many people do we have watching? I have no idea. I feel like we covered like a lot of the semester, a lot of the end of the semester. 19, I'll take it. We'll see if there's any more questions. I'll let you guys ask your final questions. Ask your final questions and we will see. If not, I'll probably head off. We'll be doing the Kahoot tomorrow. And yeah. I'm going to probably head off to my office and grab a little more food here. Any last questions? We'll be doing Kahoot. And I'm going to try to do some more reviews. 19? What's 19 mean? 19. I don't know 19. Like chapter 19? chi-square test of independence, chapter 19? Is that the exam review number 1? Which one on it? Is it the rat review question, Keaton? Is it the rat one? Sure, why not? The hardest of all the concepts. That's very subjective. The hardest question, that is so subjective. Let's do the rat one. I got a little bit of time, let's do it. I'm pulling up the question. We'll see if there's more questions in the chat. Okay, did it pull up right here? Wait, uh-oh. My Pearson might be having a problem. I've never seen that bus thing before. Come on, my Pearson. Oh, okay, now it works. It just didn't like us for a moment right there. Okay, let's take a look at it. That was weird, never seen that. Oh, 19 people watching. I did take a look, I did see that, I should have realized. 95% confidence interval. You know what we didn't do? Here's a big thing. Interpretation of intervals. Another new screen, another one. We can do this right here. I am blank percent confident that the true, let's take a break for a moment. All right, we're good. Is contained in the interval blank to blank. I am blank percent confident that the true blank is contained in the interval blank to blank. How to tell the variable type is the hardest. There you go, Terry, good to see you in here. So we have here the confidence interval interpretation, and Terry points out something really great right here, that with this interpretation, we need to make sure we're interpreting the right thing, whether this thing right here be true proportion. We'll change colors right here. So is it true proportion? What is it? We'll do some nice blue. True proportion, true mean, true difference between the mean. So all these things right here, we won't be doing true proportion right here, but it could be true mean or true difference between the means. So we have different interpretations, but don't just put true mean right there. Don't just put true, well, we won't be doing true proportion, so let's erase that because that's the last test. Don't just write that. Make sure you say, and I'm going to do it for this question, the interpretation. Practice saying these out loud. I am blank percent confident that the true something is contained in the interval blank to blank. So this question right here is a really good one for interpreting confidence intervals, because we need to take this data right here and copy it into JUMP, and let's go ahead and make our interval. I'm just copying the data right here. Remember, this is recorded, so you can slow it down. I'm going to open a new data sheet inside of JUMP. I'm going to go here to Edit, Paste with Column Names. Please notice the difference. If you don't paste with column names, it comes in as red. Knowing the variable type is very important because this is categorical and that will not analyze correctly. In this data sheet where I pasted with column names, it's blue, and that means it's quantitative, and we will get a mean confidence interval for the mean. I'm going to go ahead right here and double click the variable, click OK. I'm going to click stack to make it nice and pretty. And then we're going to do a trick. We're going to click right here and we're going to go to redo automatic recalc. By going to automatic recalc, any changes I made to this will automatically change the graphic. Here we go. Here is our output. So think, we have an interval right here. This is how long it takes the rats to run the maze. So I am 95% confident the true mean amount of time it will take the rats to run the maze is contained in the interval 45.55 seconds to 57.43. Now, if you notice, there are rats that take longer than 60 minutes, or 60 seconds, excuse me. 60 minutes is a long time. So there are rats that take longer than 60 seconds, but the average time, we believe, we're 95% confident, is contained in the interval 45.55 to 57.43. We do see an outlier here, and this is a small data set, so maybe that's going to be a problem for our nearly normal. Let's go ahead and go back and answer the numbers right here. Was it 45.33? Something close to that. 45.53. And 57.43. Make sure we got it right. I entered one of these wrong last time. 544. Yay, got it right. How does it look? how does it look? Well, there's an outlier, and so we're between graphic C and graphic D. There's the outlier right here. It's literally behind my head. Here, I'm going to hide that outlier. Outlier's back. Outlier's gone. It's just right there behind my head. So the only answers it could be are graphic C and graphic D. Let's go ahead and use jump to kind of help us figure this out. We'll make this look a little smaller right here. So what we're going to do is we notice that this is going from 20 to 100 by 5. I double-clicked the line right there. And when we change these bin widths, it's going to be a lot easier to see. And if you look at the pattern, it doesn't have this little thing right there and the little stick. It's got the pattern right here with the descending and the bump at the end. It is answer C for certain. Nope, didn't mean to click that. There it is. Now we need to look at the normal quantile plot. Now normal quantile plots can only go up and to the right. Remember how we have an outlier? It's this one. Reason being is these are the observed time in seconds. This point right here of like 80 something is the very large outlier you notice up here of 80 something, and we can see it in the jump output. It was the maximum of 90.5. So I was like, is that 80, high 80s or low 90s? It's low 90s, and that point is this point right here. These are the observed times in seconds. Notice how none of these really follow that pattern. This one's just random. Normal quantile plots, something we did way earlier on, will go up and to the right, so that's the only possible answer. Technically, this one is possible, but that is much more of a perfect normal, and it doesn't show the outlier. This one has the outlier, so it's the right answer. So what do we have? The only real problem right here is the one outlier. The normal quantile plot is relatively straight with the one outlier. Without the outlier, the conditions seem to be met, and it is unimodal and skewed to the right. There's really not strong bimodality to this. It's kind of just one. You might say, no, Brian, there's two modes, but let's play around with it a little bit and see if we see two modes or one. That looks a lot like one. If you do this, it'll look like three modes, but we try to get a nice clear view. I'd probably graph it like that, and I think it's more default like this. I know this question is a little bit subjective, which can make it harder, but this one is kind of right here. If the confidence, oh yeah, that one. The mean, I think I know what you're asking about, Annie. It's that when you collect more data, the mean could go up or down. It's not that your confidence interval will be better estimated, but the mean would go up or down. And now we go and recalculate this interval. Let's recalculate said interval. I'm going to click the point, and because I have auto recalc on, if anyone's watching this and it is not working, it's because you don't have auto recalc on. Does everyone see how everything automatically recalculated for me? If it doesn't automatically recalculate, you can go to redo analysis, and you'll get it redone. But mine had auto recalc on from earlier in the video, so make sure you see that. 4496, and I think it was, oh no. How did I hit that underline thing? Sounds like you typed too fast. You're like, what's going on? Oh, what am I doing? I can't remember numbers today. 4498, wow. Last attempt here, we got this, and this is the last one round up properly. We'll end on a high note here. Oh, look at that, we finally got it. Make sure to calculate your numbers correctly. Does it meet the 1 minute challenge? No, it doesn't. Both intervals are entirely below. This does not meet the 1 minute average challenge because both confidence intervals are entirely below a mean of this. Double check, the maze does not meet the 1 minute requirement, yes. And I want to make it very clear. When you're doing this interval right here, I am 95% confident that the true mean time it takes for RAS to complete this maze is contained in the interval 44.98 to 54.11. Does that make sense? I am using my interpretation right here to say I am 95% confident that the true amount of time it takes RAS to complete this maze is contained in the interval 44 point yada yada to 54 point yada yada. How about this right here? Not that one. Well, yeah, sure. I am 95% confident the true mean GPA of UT students is contained in the interval 3.742 to 3.789. How about this one? Not there. How about, we have done a lot of work today. How about this one right here? A lot on the screen, but let's focus in on this. I am I am 95% confident that the true difference between male and female's GPAs is contained in the interval 0.2 points to 0.29 points, where females on average had higher GPAs than males, where females mean is higher than male GPAs. So I am 95% confident the true difference between male and female GPAs is contained in the interval 0.20 to 0.29, where females have higher GPAs than males. If you notice, why is it females have higher GPAs than males? It's because the difference is negative, and that means this number is bigger on that side. If the difference was positive, then it would be males having the higher GPAs. And also I want to note, if the difference goes through 0, then 0 is a possible value. And that, I think that's got it. We've gone for almost 2 hours now, an hour and 50 minutes. Did this help people out? We're going to do the Kahoot tomorrow, so please join in for the Kahoot at noon. Hopefully we get a bunch of people in here having some fun, reviewing the questions. We'll be doing output and interpretations and all that good stuff. Any last questions before I head off? It's your chance now. Say them or forever hold your peace. Oh, we got to do it then. We can do it. Watch this. Oh, wait, that's one button. So thank you. You have trouble. There we go. There we go. We got to figure it out. So remember, Kahoot at noon tomorrow. So let's end strong. Kahoot at noon. See you guys there. Talk to you later. See you guys.